Okay, so again, recall that our change in enthalpy is going to be equal to the heat released or absorbed by a reaction as long as it is at constant pressure. So again, whenever you see these subscripts, so this is Q represents heat, and whenever it has a subscript of another variable, in this case pressure, it means that that variable is being held constant, okay? Now, the second law for spontaneous reaction at constant temperature and pressure then becomes this. Now we're talking about the system itself, okay? When a change in entropy is greater than the heat over the temperature, okay? Now remember, we could write that like this. If it's a constant pressure, well, that's the change in enthalpy. So when the change in enthalpy over temperature is greater than the change of entropy, we have a spontaneous reaction. Again, I stress that the sign of this is irrelevant. The sign of this is irrelevant at this point, right? So again, we're changing that second law into a usable fashion. The second law talked about the change in entropy of the universe, the system plus the surroundings. Now we're talking about the entropy change of just the system. Now we could rearrange that and say, okay, del H minus T del S, if it is less than 0, if it is negative, it is spontaneous, okay? So again, the signs of these don't dictate whether a reaction is spontaneous or not. It is this equation here. Its sign dictates whether or not a reaction is spontaneous. So again, if this is negative, we have a spontaneous reaction. So negative spontaneous reaction. If it's positive, we have a non-spontaneous reaction. What if it's equal to 0? What do you think that means? What do you think it means if this quantity is equal to 0?
Is it an equilibrium though?
Yeah, it's at equilibrium. Okay, so here's another way we're going to define equilibrium now. If this quantity is equal to 0, our system is at equilibrium. Now, I will tell you that, again, this really needs to be changed to less than or equal to, okay? And I might say that on the next slide. Because this is a spontaneous process, right? A system being at equilibrium is dynamic. The reaction is still proceeding in the forward direction and the reverse direction. Although the concentrations of reactants and products aren't changing, it's still occurring, right? Me just holding this pen at the same height, okay? I'm not moving it, it's at the same height. Is that spontaneous? Yeah, right? It's occurring without any other force. Now, if I let go of it, it goes up to the ceiling. Is that spontaneous? Not here on Earth. I'd have to do some force to cause it to go up to the... Okay, I will see you tomorrow. Okay, so if it floats to the ceiling, that would be non-spontaneous. I had to do work to make that occur. But if I drop it, it falls. That's spontaneous. So the idea is that equilibrium, it just sitting there, is spontaneous. Okay, so everybody gets that idea. Okay, but we're actually going to look at a new thermodynamic value now, okay? So again, here it is. So again, when it's 0, when it's at equilibrium, again, it is spontaneous. So there's our equation for spontaneity. But now I'm going to introduce a new thermodynamic quantity called the Gibbs energy, or the Gibbs free energy. Okay, the reason it's free energy, this is the amount of energy that is free to actually do work. Some energy lost is thermal energy, which is just random motion. You do not need to do partition functions in Chem 110. I can tell you that. Okay. So we have this equation. So we're going to replace this, and we're going to call this quantity the Gibbs free energy. So the Gibbs free energy is just enthalpy minus the absolute temperature times entropy. But again, we can't look at absolute values, so we're just going to look at the change in entropy. Note that this is at constant temperature. If it wasn't at constant temperature, then we're going to have to do some calculus, right? Because as the reaction changes temperature, the free energy change is going to change as well. So for those of you chemical engineering, well, of course, in real life, the temperature often does change. So yeah, the equations are going to become a lot more complicated. They're still based off the same thing. It's just that you're now going to do calculus, okay? So if we talk about the standard free energy, so in other words, we put the not here, well, that's the free energy change at standard conditions. 1 atmosphere, 25 degrees Celsius, 1 molar if we're talking about solutions, so on and so forth. So basically, we have the enthalpy of the reaction. We have the temperature in Kelvin. Now, in this case, if these are del naughts, T has to be 25 degrees Celsius, but it has to be in Kelvin. So, of course, 298.15 Kelvin. And then this is simply the entropy change. And again, we can get these by just using the enthalpies of formation and the absolute entropies and the summation laws for both of them. Okay? Now, this is just a review, basically, of what I said, except now we're talking in terms of del G. So that was that inequality that we just seen, right? It's actually called the Clausius inequality. And so when del G is negative, it's spontaneous. And to be specific, when it's large, okay, so greater than negative 10, or I should say less than negative 10 kilojoules, right? So negative 10, negative 11, negative 12, then we consider it to be a spontaneous reaction. If del G is positive, then we say that it is non-spontaneous. And generally we say that it has to be greater than 10 kilojoules to be non-spontaneous. Because when del G is small or 0, right, then basically we're at about equilibrium. And again, we say generally say plus or minus 10 kilojoules. To make life simple for yourself, we're simply going to say that when del G is equal to 0, it is at equilibrium. When del G is positive, it's non-spontaneous. When del G is negative, it's spontaneous. We're not going to worry about this caveat of plus or minus 10 kilojoules. Okay? Okay, so let's calculate. What is the standard free energy change for the combustion of hydrogen at 25 degrees Celsius? Well, the combustion of hydrogen is going to be hydrogen gas, which of course exists as a diatomic. It's one of the 7 diatomic elements, right? Again, hydrogen, nitrogen, oxygen, all the halogens, fluorine, chlorine, bromine, iodine, and astatine. So hydrogen's H2. Combustion means it's reacting with O2, okay? And it's going to form combustion products, which again are going to be carbon dioxide and water. I'm sorry, there's no carbon, so just water, okay? So there's the reaction for the combustion of hydrogen. And we want to calculate the free energy change for this reaction. So that then is going to be specifically 2 moles of hydrogen reacting with 1 mole of oxygen to produce 2 moles of water. Now we can use the values for the enthalpy of formation and the absolute entropies from the tables of chemical data. So we just need to look them up. So the enthalpies of formation for H2 is 0. And I'll get into why it's 0, either in the notes here or in the when we do some homework problems. But the enthalpy of formation of H2 gas is 0. And that's again because the enthalpy of formation is the amount of energy required to make a molecule from the elements in their standard state. Well, the standard state of hydrogen is H2 gas. Therefore, to make H2 gas from H2 gas costs 0 energy. Same thing is true with diatomic gaseous oxygen. Well, that is the elemental form. That's how oxygen exists at 25 degrees Celsius in 1 atmosphere. So it doesn't take any energy to create O2 from O2. Now, water, on the other hand, is going to be created from the H2 and the O2, and it has an enthalpy of formation then of negative 241.8 kilojoules per mole. Now, we're going to look them up for the absolute entropies. And again, since none of these are ions, they all have to be positive. So the entropy for hydrogen gas at standard conditions, 130.7 joules per Kelvin per mole. Again, notice that these are in joules and the enthalpies are in kilojoules. The O2 is 205.2 joules per Kelvin per mole, and the gaseous water, 188.8 joules per Kelvin per mole. And again, as you learned in Chem 110, the phase is very important, okay? So, for example, the enthalpy of formation of gaseous water is negative 241.8, but the enthalpy of formation of solid water is negative 280 some. Okay, so it's negative 285 to be exact. So it is greater. Okay, so it is greater. So again, the phases matter. So the phase labels really, really matter in thermodynamics. Okay, now that we've looked up all of them, we're just going to use the summation laws for the enthalpy change and the entropy change. So for the enthalpy change, it looks like this. We would plug in our values. There's the 2 moles of our gaseous water at negative 241.8. Again, the moles cancel, so that'll just have units of kilojoules. And these are both 0, so that's just going to be minus 0. So the enthalpy change is just negative 483.6 kilojoules. We'll use the summation law for the change in entropy. So again, we have the 2 moles of water at 188 joules per Kelvin per mole. The moles cancel. Then we're going to subtract from that the 2 moles of the hydrogen at 130.7 joules per Kelvin per mole, and the 1 mole of oxygen at 205.2 joules per Kelvin per mole. The moles canceling, giving us again units of joules per Kelvin. Plug that all in, that gives us negative 89.0 joules per Kelvin. Okay, so now using the enthalpies of formation and the standard entropies and the summation laws for both, we've now determined the enthalpy change and the entropy change under standard conditions. So we've already seen that the free energy change then is simply going to be the enthalpy change minus the absolute temperature times the entropy change. Now, the change in free energy has the same units as the enthalpy, so kilojoules. So we're going to want to do this and make sure that this ends up in kilojoules. So right now the temperature is in Kelvin, but this is in joules per Kelvin. We're going to need to change the joules to kilojoules by simply dividing by 1,000. Okay, so we divided this by 1,000, which gave us negative 0.0890 kilojoules per Kelvin. So we can see that the Kelvin cancel, and that leaves us kilojoules minus kilojoules, right? So whenever you're adding and subtracting, the units have to be the same. So they cancel, and it gives us negative 457.1 kilojoules. So that is the free energy change for this reaction. So is this reaction spontaneous or non-spontaneous, or is it at equilibrium? Is it spontaneous, non-spontaneous, or at equilibrium? We have a negative del G value. Negative del G. Is it spontaneous, non-spontaneous, or at equilibrium? Kaylee, what do you think? Is the reaction spontaneous, non-spontaneous, or at equilibrium?
Would it be spontaneous?
Yeah, right. When delta G, when the free energy change is negative, we say that the reaction is spontaneous, right? So this reaction is spontaneous. Okay. Okay, now we actually didn't need to go through all of that. Okay, since it's at 25 degrees Celsius in 1 atmosphere, there's actually another summation law that we could use that uses the standard free energy of formation. So del G Fs, just like the enthalpies of formation, there are free energies of formation as well. Okay, and we can use a summation law for that. And again, these free energies of formation can be found in tables of chemical data or in the appendix of your text. And again, it's the same summation law. It's going to be the free energies of formation of the products, each multiplied by the coefficient in the balanced chemical equation, minus the free energy of formation of the reactants, again, each multiplied by the coefficient in the balanced chemical equation. So let's do it again. This time, let's calculate del G for the reaction of 1 mole of sulfur dioxide with excess hydrogen sulfide to form gaseous sulfur and water vapor. So that looks like this. Okay. So we're simply going to look up the free energies of formation for each of these in that table. Okay, we're going to find them in the tables of chemical data. So there they are. Okay, we just looked them up. Notice that they're in kilojoules per mole. So these are the molar quantities. We're going to plug them into the summation law. So we have the 3 moles of the gaseous sulfur at 236.7 kilojoules per mole times the 3 moles. The moles cancel, and that gives us units of kilojoules. Then the 2 moles of water at negative 228.6 kilojoules per mole. Then we're going to subtract from that the 1 mole of sulfur dioxide at 300.1 kilojoules per mole. So the moles cancel. And then plus the 2 moles of hydrogen sulfide at negative 33.4 kilojoules per mole. Moles again cancel. So that gives us then 619.8 kilojoules. So is this reaction, Leah, is this reaction going to be spontaneous, non-spontaneous, or at equilibrium?
Is that non-spontaneous?
That is definitely non-spontaneous, right? We have a large del G value.
Now, for equilibrium, is that just equal to 0?
That's going to be equal to 0. The reality is we would consider equilibrium to be basically plus or minus 10 kilojoules. But let's just keep it simple. We're going to say equilibrium is 0.
Okay, so thank you.
If I tell you it's plus 10 kilojoules, the reality is I would accept either it is non-spontaneous or at equilibrium. So
all right,
if you do use that idea, I will again grade it both ways.
Okay.
Okay. Okay, so this then is a non-spontaneous reaction. It's simply not going to happen. Okay. Now, can it happen? Yeah, but we'd have to add energy to the system to force this non-spontaneous reaction to occur. Okay. Okay, now I want to talk about maximum work. So I keep calling this thing the Gibbs free energy. Well, that is the amount of energy from that chemical reaction that is available to actually do work. Okay. So, for example, a spontaneous precipitation reaction occurs. The free energy of the system decreases and the entropy is produced, but no useful work is actually obtained. Okay. So no useful work is obtained from a precipitation reaction. Now you can think of, well, what if I put a balance inside the solution and the one plate is in the solution, the other plate is out of the solution, and I put a feather on the one that's on the outside, and then I do a precipitation reaction. Well, I'd have to precipitate a lot of salt for that salt to land on that balance and lift that feather a little bit, right? So you can see where a precipitation reaction is going to not result in much useful work. So the maximum work, the maximum amount of useful work is simply going to be equal to the amount, the free energy change that occurs. Now I'm going to talk about this on, what is today, Wednesday? Let me see, is today Wednesday? Yeah, so I'm going to talk about this tomorrow more, but you got to be careful. There's del G, there's del G naught. There's del G naught F, there's del G M, okay? All of those little subscripts and superscripts mean something different. This del G right here means this is the free energy system of that given reaction, of that amount of material, reactants and products that were formed, okay? So this isn't a molar quantity. This value would have units of kilojoules, not kilojoules per mole. So we'll talk more about that because that can be very confusing. There's at least 5 different del G's, and they all have very different meanings depending on what the sub and superscripts are, okay? So that is maximum work. And again, this is where the term free energy originates, is the fact that's the amount of energy that's actually useful to us. Now, this is simply an overview of everything that we talked about. I do not expect you to memorize this. I expect you to be able to reproduce it, okay? And the problems, the homework problems are going to expect you to be able to reproduce this, okay? Because you're not going to have this when you take the exam. You need to be able to tell me. So for example, if del H is negative, so this is a negative value, and del S is positive, what's the sign on del G? Well, if this is negative, and this is positive, and then this term is negative, well, a negative and a negative is got to be negative all the time. So if I have an exothermic reaction with an increase in entropy, the reaction is going to be spontaneous at all temperatures, no matter what.
Quick question.
Yeah.
What do you mean by reproduce? Like just know the equation or this whole table? Like, what do you mean by reproduce this?
The idea. You'll understand. You'll definitely understand once we start doing the homework problems.
Okay.
If I tell you you have an exothermic reaction and an increase in entropy, you should be able to tell me the sign of del G. And then the sign of del G, of course, dictates whether or not the reaction is spontaneous or not, right?
Yeah. Okay.
So let's look at another example. Let's say that the del H is positive, okay? I'm just going to change the animation on this. Okay, so if del H is positive, right, we have an endothermic reaction. And we have a loss in entropy. Del S is negative. Well, this is negative and negative, so this term is positive. This term is positive. So in other words, at any temperature, this is positive. So that means that this reaction is not spontaneous at any temperature, because del G is always positive. So it's got to be non-spontaneous at any temperature. But what if we have an exothermic reaction, this is negative, and we have a loss in entropy, so this is negative. Well, now I have a negative term, but now I have a negative and negative, which is positive. So that means this term is negative, this term is positive. So if this term dominates, then del G will be negative, and the reaction will be spontaneous at low temperatures. Because if I raise the temperature, then this negative and negative positive, if I raise the temperature, this positive term is eventually going to be greater than this negative term, and the change in free energy is going to be positive, and therefore it's going to be non-spontaneous at high temperature. Okay, does that make sense? This is what I'm going to expect you to be able to do to understand this. Let me give you another example. If I have an endothermic process, so this term here is positive, and I have an increase in entropy. So this whole term then is negative, right? This is positive, this is negative. So at low temperatures, when this term is small, this negative term is small, this is going to be greater positive. So this is going to be positive, and we'll have a non-spontaneous reaction. So non-spontaneous reaction this time at low temperatures. But if I raise the temperature, this negative term is going to become larger than this positive term. And so del G is going to be negative, and therefore spontaneous at high temperature. Okay, so do you see what I mean by being able to reproduce this thing? You should easily be able to do it by simply looking at the sign of del H and del S. So the only time it really matters is when they both have the same sign. Then you have to worry about temperature. Okay. Okay. Now, if we assume that both del H and del S are essentially constant with respect to temperature, they kind of are. They're not. They're temperature dependent. If we would change the temperature greatly from 25 degrees Celsius, these values will start to change. But we're going to assume that those values don't change with a change in temperature. That means we're going to be able to use that equation for the standard free energy change, where del H minus T del S, right? We're going to be able to use that equation to determine then free energy changes at non-standard temperatures. So in other words, at temperatures other than 25 degrees Celsius. Now, we're going to add a subscript of capital T. So when you see del G naught T, it means we calculated the change in free energy from the standard enthalpy and entropy change at 25 degrees Celsius, 1 atmosphere, 1 molar. But we did it at a non-standard temperature. So when you see this, you know that there's going to be some uncertainty in del G. Otherwise, if I calculate del G naught at 25 degrees Celsius, it's actually going to be very accurate if I just use the enthalpy change and entropy change under standard conditions and summation laws. But once I start changing the temperature, so this isn't 25 or 298.15 Kelvin anymore, this number is going to start to become less and less accurate as the temperature deviates more and more from 25 degrees Celsius. Okay, so that's why we got the del GT there. So let's try this then. So it says hydrogen cyanide can be released when gaseous methane and ammonia are combined. And we want to find the del G for this reaction at 25 degrees Celsius, and then the second time at 1,525 degrees Celsius. And we want to relate the spontaneity of this reaction, or determine the spontaneity of this reaction at these two different temperatures. Okay. So here's our chemical reaction. We got the methane reacting with ammonia to produce hydrogen cyanide, and 3 moles of hydrogen gas are produced as a byproduct. So you'll need the balanced chemical equation to do this. Now, at 25 degrees Celsius, we could just use the free enthalpies of formation in that summation law. But since we are going to have to calculate it at a non-standard temperature anyway, that would just actually be a whole nother calculation that I'd have to do. So I'm just going to calculate the free energy change using the equation del H minus T del H, or T del S. So I am simply going to calculate then the change in enthalpy from the enthalpies of formation and the change in entropy from the absolute entropies. So I'm going to have to look up those values in the tables of chemical data for each of the reactants and products. We're going to throw it into our summation law, where we have 1 mole of hydrogen cyanide at 135.1 kilojoules per mole and 3 moles of hydrogen at 0 kilojoules per mole. We'll subtract from that then the 1 mole of methane at negative 74.6 kilojoules per mole and the 1 mole of ammonia at negative 45.9 kilojoules per mole. The moles cancel, okay? We have mixed operations, so if you're following sig figs, keep that in mind. Plug it in, and we get a del H of 255.6 kilojoules. So it's an endothermic process, right? It's positive. It's an endothermic process. Okay, we're going to do the same thing now to determine the standard entropy change. We're going to look up the absolute entropies in the tables of chemical data for each of the reactants and products. We're going to plug them into the summation law. So again, the 1 mole of hydrogen cyanide at 201.8 joules per Kelvin per mole, the 3 moles of hydrogen gas at 130.7 joules per Kelvin per mole. The moles cancel, leaving us with units of joules per Kelvin. And then we're going to subtract from that the reactants, the 1 mole of methane at 186.3 joules per Kelvin per mole, and the 1 mole of ammonia at positive 192.8 joules per Kelvin per mole. The moles cancel, again, leaving us with joules per Kelvin. We add them together, and that's going to give me 214.8 joules per Kelvin. But I already know in advance, right, that I'm going to have to plug this into the equation del H minus T del S. Since del H is in kilojoules and del G is generally in kilojoules, I'm going to change this to kilojoules. So I'm going to divide by 1,000. So it's going to be 0.2148 kilojoules per Kelvin. Okay, so now I can plug it into the equation for the free energy change with respect to the change in enthalpy and the change in entropy. So I'm just at 25 degrees Celsius. I'll plug these two values in. This got to be in Kelvin, so 25 plus 273.15 is 298.15 Kelvin. That is going to give us a value of positive 192 kilojoules. So Eugenie, is this reaction at 25 degrees Celsius spontaneous or non-spontaneous? At 25 degrees Celsius, spontaneous or non-spontaneous?
It'd be it would be non-spontaneous.
It would be non-spontaneous because it's a positive del G, so it would be non-spontaneous. So at 25 degrees Celsius, this reaction would be non-spontaneous. Now, I'm going to throw another caveat in here. What does non-spontaneous mean to a chemical reaction? Well, remember, it deals with equilibrium. So non-spontaneous simply means the reactants are favored over the products. So that doesn't mean that no hydrogen cyanide or hydrogen was produced. It just means there's more reactants than there are products, okay? So I'll throw that in there to make it even more complicated, but that's the way it is, okay? So again, it's non-spontaneous. So basically the reactants are favored over the products. Okay, so at 25 degrees Celsius, we see that it is non-spontaneous. But let's do it again at 1,525 degrees Celsius. Again, got to be in Kelvin, so we're going to add 273.15 to that. So it's going to be 1,798.15 Kelvin. Plug it into our equation. Okay, that's going to give me a value then of negative 130.6 kilojoules. So again, now we see we have a negative value. So now it's going to be spontaneous. So we can see that in this particular case, right, we had, I should put those values on there, 52. So we can see we have an endothermic reaction with an increase in disorder. So we can see that at high temperatures, it's spontaneous, and at low temperatures, it's non-spontaneous. Okay, so again, this is what I would expect you to predict for this type of reaction. Now, what is high and low temperatures is completely relative to that particular chemical reaction. Okay, a low temperature might be 500 degrees Celsius, and a high temperature 15,000 degrees. Well, let's don't go that high. Let's say 5,000 degrees Celsius. So what is high and low is relative to that particular chemical reaction. Okay, it doesn't mean that it's above or below any certain temperature. It's just relative to that chemical reaction. So again, we can see that it is non-spontaneous at 25 and spontaneous at 1,525. But at what temperature does it become spontaneous? Okay, so that would be interesting to know. Well, we can figure that out quite easily, right? So when del G is equal to 0, we're at equilibrium. That's where it goes from being spontaneous to non-spontaneous, or non-spontaneous to spontaneous in this case, okay? So if I have an endothermic reaction, I'm calculating the minimum temperature for spontaneity. We could also do this for an exothermic reaction, but if I do it for an exothermic reaction, we're actually calculating the maximum temperature of spontaneity. So this is endothermic, so we're calculating the minimum temperature for spontaneity. We're simply setting this equation equal to 0. Okay, so I'm going to set this to 0. Now on your exams, I want to see you absolutely say this. I want you to tell me that del G T is equal to 0 so that I know that you understand what you're doing. Okay, so by setting that to 0, we're saying this is the temperature then at which this reaction is going to go from being spontaneous to non-spontaneous, or vice versa. Rearrange the equation and it looks like this. So for an exothermic reaction, like I said, this would be the maximum temperature of spontaneity. For an endothermic reaction, it's the minimum temperature of spontaneity. So now we're simply going to plug in our values for del H and S. And that gives us a value of 1,190 Kelvin, or in degrees Celsius, would subtract 273.15. So at 917 degrees Celsius, it becomes spontaneous. So at temperatures of this, at this temperature and greater, it is spontaneous. Below this temperature, it's non-spontaneous. And again, as we're going to see, that means that the products are favored at a temperature of 917 degrees Celsius or higher, and the reactants are favored at a temperature less than 917 degrees Celsius. Okay. Okay. Now, I just said that. Next, I want to talk about spontaneity. Okay. So with spontaneity, we know that the second law says that a chemical reaction is spontaneous if the entropy of the universe, so that's the system plus the surroundings, if the entropy of the universe is positive, a chemical reaction or any physical process will occur spontaneously. However, it's impossible to measure the entropy change of the surroundings. We can measure the entropy change of the system, but the surroundings is just too big. That's basically everything in the universe. So we can't measure that change in chaos, but we can for the system. So Clausius actually came along and said, well, we can have a spontaneous reaction if the sum of the enthalpy minus the absolute temperature times the entropy change of the system is less than 0. So in other words, if it's negative, it's going to be spontaneous. Okay, so spontaneous. Now later on, we changed that. We said, well, if it's less than or equal, if it's equal to 0, nothing happening, or a chemical reaction being at equilibrium, is spontaneous. So it's got to be less than or equal to 0 to be spontaneous. But we then gave this term a new thermodynamic value, and we called that the Gibbs free energy, which I will often just call free energy. So we said that del G is equal to del H minus T del S. And if we're measuring these at standard state, that means the free energy must also be at standard state. So 25 degrees Celsius, 1 atmosphere, 1 molar if we're talking about solutions. So we could actually have calculated the del G for our reaction, right, of the methane reacting with oxygen, so the combustion of methane, to form carbon dioxide and water vapor. Okay? Because we determined for this reaction, right, we determined that del H was 802.5 kilojoules, and that del S was negative 5.3 joules per Kelvin. Okay. Now, from these values alone, can we say anything about the combustion of methane? In other words, is it spontaneous at any temperature? Is it not spontaneous at any temperature? Is it spontaneous at high temperature, or is it spontaneous at low temperature? Can anybody tell me that? Can anybody answer that question?
It's definitely spontaneous. I think it's pretty much spontaneous at any temperature.
Okay, what if the temperature was really high?
No, I guess it wouldn't be. So it'd be spontaneous at low temperatures, because
That's right.
at high temperature would change that S value.
Exactly, right? Because del G has to be negative.
Yeah.
So if this value is negative, well, that's negative. But if this value is also negative, that means negative times negative is positive. This is a positive term. So at some really high temperature, really high temperature, this positive term is going to dominate and the reaction won't be spontaneous anymore. So for example, methane won't burn on the surface of the sun. It's too hot, which I know sounds weird, but that's the reality of it. Okay. Okay. So, so in this case, then del G is going to be equal to negative 802.5 kilojoules. Okay. We're going to subtract from that the absolute temperature. Now, in this case, since we're talking about standard conditions, that's 25 degrees Celsius, or 298.15 Kelvin, right? We just added 273.15 to 25. Then we have this guy here, but I need to divide him by 1,000 because the units of free energy are generally given in kilojoules, the same as enthalpy. This is in joules. So I need to convert that. And I'm simply going to divide that number by 1,000. So that's just going to be negative 0.0053 kilojoules per Kelvin. So now I can see that my Kelvin cancel. I have mixed operations here. I'm assuming that my 25 degrees Celsius was exact. And so this is going to be negative. This sum here is going to be negative 1.580 kilojoules. We just have 2 sig figs, so that goes right there. Okay. So then we have the negative 802 and then plus, right, because it's minus plus the 1.5. And so the del G then is going to be negative 800.919 kilojoules. We're 1 passed and we're 1 passed, so this will be 1 passed. So the free energy change of this reaction is 800.9 kilojoules. So there's our free energy change that we determined from the enthalpies of formation, or the summation for the enthalpy of the reaction, and again, using the summation law, the entropy change for this reaction. Okay. So any questions about that? Now, we could have also used another summation law, right? We could have used the enthalpies of formation. So we could say, hey, look, the standard free energy change is going to be equal to the sum of the free energy change of formation of the products again, each multiplied by the coefficient in the balanced chemical equation. And then we're going to subtract that by the free energy of formation of the reactants. And again, each multiplied by the coefficient in the balanced chemical equation. So just as we did before, we're going to look up the free energies of formation, which will be in kilojoules per mole. So in the tables of chemical data or the appendix of your book. And the free energy of formation of methane is negative 50.4. Now, just like the enthalpies, the free energies of formation of the elements in their standard state are going to be zero. Again, it doesn't take any energy to create O2 gas from O2 gas. So this again is going to be zero. We'll look it up for CO2, which is negative 394.4, and for gaseous water, negative 228.6. So now we can plug these values into our summation law. So for the products, we had the 1 mole of CO2 at negative 394.4 joules per mole, kilojoules per mole. And then the 2 moles of water at negative 228.6 kilojoules per mole. We'll subtract from that the reactants. So that's the 1 mole of methane. At negative 50.4 kilojoules per mole. And then add to that the 2 moles of oxygen. But again, we seen that that was zero. So you don't have to show me this. I'm simply showing you this step because I want you to understand about the coefficients going with each one of these values. Okay? Okay, so that's just gone. The moles cancel everywhere. Again, we're going to have mixed operations. So if you're following sig figs, this is going to be 394.4 kilojoules. And then we have, now I'm going to write minus because this is minus. So minus and then 2 times the 228, which is going to be negative 457.2 kilojoules. And then we're going to subtract from that our negative 50.4 kilojoules. And then this guy here was 4 sig figs, so that'll put it there. So plug that into your calculator and you're going to get a value of negative 801.1 kilojoules. And that'll be to the 1 sig fig, so negative 801.1 kilojoules. Now, these two numbers are virtually the same. Okay? They're virtually the same. And that's because the free energy of formation, just like the enthalpy and entropy, was a state function. It didn't matter what path we took, whether we took this path, or in the case of the summation law, remember what that represents. That represents a whole bunch of reactions that form each one of these elements, right? So the enthalpy of formation reaction for the methane would have been carbon, which would have been our graphite, that's its elemental, right? Plus hydrogen, which is a diatomic and a gas, to produce the 1 mole of gaseous methane. And again, there's going to be 2 of these. And so that enthalpy of formation is what we determined, well, in this case, the free energy of formation was what we just determined to be the negative 50.4 kilojoules. And then we did this for each one of these, right? We had an enthalpy of formation reaction for each one. And then basically by taking this minus sign, we're flipping the reactants, right? We would have flipped this reaction and therefore flipped the sign. That's why the negative sign. So basically, Oh, shit. You guys got to tell me when you can't see. So again, there's the enthalpy of formation for the free energy of formation for the gaseous methane. So again, using Hess's law, where we just add all of these different reactions together, if I flip the reaction in thermodynamics, right, all I did was flip the sign. And that's exactly what this equation does, is it flips the reaction and flips the sign. And then the n is changing the exponent so that when we add all of the enthalpy of formation reactions together for these reactants and products, we basically get this overall reaction. And so the summation law just simplifies all that for us. Okay, any questions about that? Okay, now we also said that the Gibbs free energy is the maximum amount of work that we can get out of a chemical reaction. Now keep in mind, this is for a spontaneous reaction. And I'll make this more clear when we do an example of this later, okay? If it's a non-spontaneous reaction, this equals 0. No matter what the value of del G is, right? So that's going to be a positive value of del G, because a positive value of del G is non-spontaneous, and a spontaneous del G is negative. Non-spontaneous del G is positive, right? So no matter what the value of del G, if it's positive, max work is equal to 0. You can't get any work from it because it's a non-spontaneous reaction. For a spontaneous reaction, it's going to be whatever the calculated value of del G is. Okay? Okay, we then also talked about reactions at non-standard temperatures, right? We had an equation relating the enthalpy change and the entropy change under standard conditions, so 25 degrees Celsius in 1 atmosphere, but what if we're not carrying our temperature out at exactly 25 degrees Celsius? Well, we can still use this equation, but because the enthalpy and entropy are slightly temperature dependent, there's going to be some error to it. To indicate that error, we're going to add the subscript T, which means we calculated the free energy from the standard enthalpies and entropy changes, but not at the standard temperature. The further away you are from 25 degrees Celsius, the more error is going to be in this number. Now, what we haven't talked, 29, it says, for each of the following, state whether the reaction is spontaneous or non-spontaneous as written, or is easily reversible. So easily reversible is going to be a reaction that where at equilibrium, you have equal amounts basically of reactants and products. So is this first reaction here, is it going to be spontaneous or non-spontaneous? Hannah, what do you think?
It'll be spontaneous.
Right. We have a large negative del G value, so this thing is going to be spontaneous. Okay. Taylor, what about this next one? What do you think about it? Spontaneous, non-spontaneous, or easily reversible?
Non-spontaneous because of the positive delta G.
Okay, I'd give you that, but I want to add a caveat to it. I mean, I would give you credit for that, okay? But the better answer is easily reversible. That's because it's within that range of plus or minus 10 kilojoules. So when this is close to 0, we say it's an easily reversible process. Okay. That's why most phase changes, that's why we call phase changes easily reversible. If you look at the enthalpies of vaporization, condensation, they're all pretty close to zero. Okay, they're not big, they're not large numbers. Okay, and then finally, Jada, what about this last one? Is it going to be spontaneous or non-spontaneous? I think we lost Jada. Eugenie, what do you think?
Non-spontaneous because
Right. Yeah, it's a large positive value, so it's going to be non-spontaneous. Okay, any questions about that? Again, just basically, if it's a large negative number, if the free energy is a large negative number, it's going to be spontaneous. If it's positive, it's going to be non-spontaneous. If it's close to zero, it's going to be easily reversible. And we will use the term equilibrium, especially when we're calculating del G from Q, from the reaction quotient. Okay, so we could say equilibrium, or we could say easily reversible. Remember, these values are assuming we are starting off with just reactants and going to equilibrium, right? We're starting off with reactants and going to equilibrium. The free energy change of getting from just reactants to equilibrium is that number there. Okay. Okay, so this time for each of the following processes, indicate the sign of the enthalpy, entropy, and if possible, indicate the sign of the free energy change. So we're looking for del H, we're looking for del S, and we're looking for del G. So, again, the easiest way to solve these is to write a chemical equation for it. What chemical equation would you give for dew forming on leaves? What chemical equation would you give for dew forming on leaves?
Water going from the gaseous state to the liquid state.
Absolutely, right? So it's water vapor in the air going to condensing to liquid on, in this case, the leaves, right? So what would be the sign of del H for this process? We got to give up heat or gain heat to go from a gas to a liquid? Heat, of course, is just energy.
do you give
I can't hear you.
I said, do you give up heat?
Yeah, right. Remember, we got to get this, the gas molecules have a tremendous amount of energy. So we got to get rid of that energy so that the intermolecular forces could hold them together as a liquid. So what sign then is del H going to be?
Negative.
Negative. How's the entropy changing? Are we gaining disorder or losing disorder?
Losing disorder.
We're losing disorder, right? It's going from very disordered to ordered. Now, how are you going to tell me about del G? What are you going to think of when you try to give me the sign of del G?
The energy left to do work. Right.
Say that again.
I think that's the energy left, the free energy left to do work.
Well, yeah, absolutely. That would be the definition of del G. But how would we go about predicting the sign of del G?
I'm not sure. I don't remember.
Well, how's enthalpy, entropy, and del G related?
So it can either be spontaneous or non-spontaneous.
Well, yeah, but I want to know that. I want to know if you can predict the sign of this reaction. The sign of del G.
Well, Just in this question, no, because I think we need to know the temperature.
Okay, but
No.
why? How do these relate? How do these variables relate to one another?
So like if it's I think it's spontaneous. If they're both negative, it's spontaneous at a low temperature, but not at a high temperature. Is that what you're asking?
Kind of, no, not really. I mean,
Okay.
yes, that is the final answer that I want. Maybe, I don't know. I'm trying to get, what is the relationship between these variables? How do we relate variables to one another? We do it in an equation, right? Is there an equation that relates these variables? Right? So the change in free energy is equal to the change in enthalpy minus the absolute temperature times change in entropy. So if this is negative and this is negative, what were you telling me about del G? When will it be spontaneous? What sign do I want for it to be spontaneous?
You want a negative for it to be spontaneous.
Negative, right? So spontaneous. Now, do you need to tell me anything more about that? Is it always spontaneous?
At a low temperature.
Yes, right. So it's going to be spontaneous at low T. Because again, this is a positive term because of the negative and negative. So the higher the temperature, the bigger the positive term until finally it's bigger than the negative term and del G is positive and therefore non-spontaneous. Does that make sense to everybody? Okay, let's do it again. This time we have the tungsten solid going to tungsten gas. So, Hannah, what do you think? What's del H going to be?
It'll be positive.
Yep, because I'm going to add energy. I have to overcome the intermolecular forces holding these tungsten atoms together so that they can escape into the gas phase. So I'm going to have, this going to be positive. What's del S going to be?
It'll also be positive.
Yeah, I'm going from something that is very ordered to something that is very disordered. So these numbers are both going to be very large in this case. Then what about del G? When will it be negative? When will it be spontaneous? Ever?
At high temperatures.
At high temperatures. So it's going to be spontaneous at high T. And again, that's because the del G, since del H is positive and del S is positive, well, that's always going to be positive. This term will be negative. And if we want this to be negative, then the temperature is going to have to be high. And again, what that means is relative to the chemical reaction that's occurring, okay? In this case, high temperature, we're talking in excess of like 3,000 degrees Celsius, okay? So that's what high temperature means for this chemical reaction, okay? Okay, paint drying. What chemical reaction are you going to give for paint drying?
It'd be paint going from a liquid to a solid state.
Okay, so I could write water if it's water-based paint, or if it's a solvent, whatever that molecule is, it's going from a liquid, it's evaporating off to form what? Is it becoming a solid? See, this is a little bit more complicated one, but the solvents actually go into a gas. Now, the solid particles in paint's a suspension. It's not a solution. So the particles suspended in the paint always are solid. So they never actually undergo a phase transition. They just lose the liquid. Okay. So does that make sense? Okay, Eugenie, what's del H going to be?
It's gaining heat, so it will be positive.
Okay, del S?
Less disordered. Positive.
It's gaining disorder. And then under what conditions then will this reaction be spontaneous?
At high temperature.
So again, at high temperature, right? It's the exact same idea that's happened here. So at high T. Okay. Any questions about that? Okay, let's try another. So this is number 1834 from your homework. It says the free energy of formation of 1 mole of compound refers to a particular chemical reaction. For each of the following, write that equation. So I have potassium thiosulfate. What is the chemical reaction that represents the free energy of formation? So we're looking for del GF, right? What chemical reaction represents del GF? Anybody want to tackle that one? Keenan, I'm so glad you volunteered.
So is that just this? That's the formation, right?
That's correct.
So is that the?
So what do you know for sure right off the bat?
That we have 1 mole of each compound, or
Oh, you're on the right track, but what do you mean by that? So there's my compound, 1 mole of it. It's a chemical reaction. So is it going to be a reactant or a product?
is that the product? Because
That
it's
is the
formation of 1 mole.
Right? The formation. So it is the product.
Yeah,
And if you keep saying 1 mole, which is absolutely correct, this coefficient is going to be 1, period.
yeah.
And it's a solid, so we're going to add that.
Mhm.
Okay, so what are the reactants going to be?
Would it just be the potassium and the thiophosphate?
Absolutely not.
Okay.
The reactants are the elements in their standard state. So I have potassium, I have sulfur, and I have oxygen.
Okay.
So how does potassium exist? Monatomic or diatomic? Those are your only 2 choices, right?
Yeah. I think is it monotonic?
Right? So is it one of your diatomics?
I don't think so.
What are your diatomics? Starting over here, going that way. What are your diatomics?
It's your hydrogen, your mercury.
Nope.
No.
Mercury +1 is an ion.
Oh, okay.
That's a that is a polyatomic ion. Not. Okay. There will be no ions in the reactants. Everybody hear me? There will never be any ions. Every single one of your reactants will only contain 1 element. If you have any kind of molecules over here, it's wrong. If you have any kind of ions of any kind, it's wrong. These are always going to be neutrals, the elements in their standard state. So hydrogen's a diatomic. What else? What other elements are diatomics?
I think, is it oxygen, nitrogen? Is it like the oxygen, nitrogen, fluorine?
The whole row.
Whole row
So it's
down.
just hydrogen, nitrogen, oxygen, and all your halogens.
Yeah.
Okay, so is potassium a diatomic?
It is not.
What phase label does it get?
It gets a solid.
Why?
Well, it's a metal and it's not colored red.
Exactly, it's black, right?
Yeah.
If it's black, it's a solid. Okay, is sulfur a diatomic?
No.
No, it's not one of those. And what phase label do I give it?
I get a solid as well.
Again, it's black, so it's a
Yeah.
solid. Is O2 a diatomic?
It is a diatomic.
It is. What phase label do I give it?
That's gas, right?
Yeah, because it's
Yeah.
red. So it's gas. Okay, now all I need to do is balance it. What do I put in front of the K?
It's going to be 2.
2. There's 2 of them.
Yeah.
In front of the S.
2.
2 again. There's 2 of them. In front of the oxygen.
Now you can have fractions in here, right?
That is absolutely correct. One of the few times you're allowed to have fractions in a balanced chemical reaction.
So I'm going to get 3. I'm trying to think. Would it be, would you put, it would be like 6/2? Would that give you 3?
Okay, 6
Or
of
am I way overthinking this?
it's actually, yeah, much easier. Whenever you have an element by itself, and you
Mm-hmm.
always will in these either enthalpy of formation or free energy of formation,
Yeah.
all you have to do is take the number of oxygen on the other side, which is 3, and divide it by whatever that is, which
Okay.
is 2. So there it is. It's now balanced,
Okay.
right? 2/3, if I divide it, so I got 2/2, that will be 3.
Okay.
Which gives me my 3. Okay. And if I wanted to make this a balanced thermochemical equation, let me see if I have that value. I do not. I'm making up a number. This number is completely bogus so that you all know. If I wanted to make this a balanced thermochemical equation, I would simply say that del G, and this is at standard temperature, is some value. And now I'm making up this value. I don't know the value offhand, but let's say it's negative 423.8, and it would be kilojoules. Now, when you looked it up in the book, it would look like this. It would look like negative 423.8 kilojoules per mole. And again, the reason they're giving it to you in a per mole, because it means for the formation of 1 mole of that particular substance. Okay, any questions with that? Okay, let's see. Who wants to volunteer for the next one? Taylor, absolutely. You must insist. So, what is the balanced chemical reaction for the free energy of formation of phosphorus pentabromide? Tell me the easy parts.
Well, the PbR5 is going to be the product.
Absolutely. What coefficient?
1.
And it does not change. Phase label?
Gas.
Yeah, it was given as a gas, so gas. Okay, reactants?
P.
Okay, is that monatomic?
Yes.
Sorry, let me do this for you. So that is monatomic. And what phase label is it going to get?
Solid.
It's black. It's going to be a solid. What about Br?
Br is diatomic.
That's right. It's one of our diatomics. What phase label does it get?
Liquid.
It's blue. And I know it's kind of hard to see, but it's blue. And it's a liquid. What coefficient do I put in front of bromine?
The 1/5.
Not 1/5. I'm going to take the coefficient from the product side, put it in the numerator, and then divide it by that number.
Oh, okay.
Okay. So think of it this way, right? I have 5 times 2, that's 10 bromines divided by 2 is 5.
Can you go over how you know if it's diatomic or monatomic?
There's only one way to know. That is to memorize them. What are my diatomics? What elements are my diatomics?
Bromine.
Okay. I'm going to make this more, I'm trying to make this more systematic. It's hydrogen,
Mm-hmm.
nitrogen, oxygen, all the halogens.
Okay.
Hydrogen, nitrogen, oxygen, all the halogens. So with the periodic table, it's easy, right? It's only these three and then this column.
Okay. Yeah, I get it now.
Now I'll tell you, in reality, they don't say that astatine is a diatomic. It's one of those man-made elements that only exist for literally femtoseconds.
Mm-hmm.
So they've never actually been able to make two at once. So they're not sure if it's diatomic, but again, it probably is if they could actually make enough of it.
Okay.
Okay. But again, it's hydrogen, nitrogen, oxygen, and the halogens.
Okay. Thank you.
Okay.
Are all the red ones all gas?
Yep. Those are the gases at 20. Now remember, this is at standard conditions, 25 degrees Celsius in 1 atmosphere. And again, this is the periodic table that I've given to you on Canvas. It says for use on quizzes and exams. This is the table. If you were really in my class, this is what you would get. These are what the periodic tables on the walls in the room look like. Okay. Okay. Yeah, so the reds are gas, the blues, which are only bromine and mercury, are liquids at 25 degrees Celsius in 1 atmosphere, and everything else at 25 degrees Celsius in 1 atmosphere is solid. Now there are allotropes, right? Like carbon has 4 solids. It has graphite, diamond, graphene, and fullerenes. But the standard state is graphite, coal, right? So graphite. But again, I would simply accept solid. Okay. Okay. So any more questions on that good stuff? Everybody good with that? Okay, let's try another question then. This is number 39 from chapter 18. It says, what is the maximum work that can be obtained from the reaction of 5 grams of zinc metal in excess acid at 25 degrees Celsius given the following reaction? So how am I going to determine the maximum amount of work?
The free energy is equal to the maximum amount of work.
Okay, so free energy, let me write this down here. So free energy is equal to work max. So how do I calculate the free energy then?
Isn't the summation of the product free energy minus the reactant free energy?
Okay, so you want me to use a summation law that the change in free energy is equal to the sum of the free energy of the products, again, each multiplied by the coefficient in the balanced chemical equation, minus the sum of the free energy change of the reactants, and again, each multiplied by the coefficient in the balanced chemical equation. Okay, so I will look them up. So the free energy changes, I will look in the tables of chemical data. And now I noticed that zinc solid, okay, zinc solid, looking at my periodic table, zinc solid, that's the elemental form. So what's the free energy change for it?
0.
0. It doesn't take any energy to create zinc solid from its elemental form, zinc solid. So it's 0. So I can save myself time by knowing that, right? I don't have to look in the book. I do have to look up H plus aqueous. it's actually 0 as well. That ends up being for bookkeeping reasons. Zinc 2 plus is not zinc solid, so I'm going to have to look up what the value it is, what the value is for zinc 2 plus, and it's negative 147.1. And then again, I noticed that the hydrogen gas, well, isn't that the elemental form? It's a gas, it's a diatomic, so that's its elemental form, so it's 0. So you can save yourself a lot of time from trying to look these things up in tables, okay? Okay, so now that we have that, well, this is going to be real simple. I have my products, so there is 1 mole of that. So there's 1 mole, and it is at negative 147.1 kilojoules per mole. The rest is 0, so plus 0, and then minus 0 plus 0, because they're all zeros. So in the end, this is simply going to be negative 147.1 kilojoules. Okay, so is that the answer?
No, because you have to find the number of moles of the zinc metal and then multiply it by that, because that's only for 1 mole.
Yes. Okay. Now, you keep saying 1 mole. Where's that 1 mole coming from?
Well,
There's no moles. There's no moles in this. This isn't per mole. And that's why I keep cautioning you guys. When you do these summation laws, the units are
they cancel.
kilojoules. So how can you relate it to the zinc, the number of moles of zinc? We have to write the balanced thermochemical equation so that we can relate energy to the coefficients in that reaction, right? How do I write a balanced thermochemical equation? I simply add this thermodynamic value to the end. Del G equals negative 147.1 kilojoules. Now I can relate that energy to the number of moles of any of my products or reactants. So now to calculate del G, the actual free energy change, I'm going to say, well, there is 5 grams of zinc. Zinc has a molar mass, so in 1 mole of zinc, there is 65.409 grams of zinc. The grams of zinc cancel. Now, using my molar energy ratio for my balanced thermochemical equation, I need moles of zinc to cancel. And I'm interested in the energy, which is going to be in kilojoules. So I can see for every 1 mole of zinc, 147.1 kilojoules of energy is released, or in other words, negative 147.1. The moles of zinc cancel, excuse me, and plug that into my calculator, and that gives me negative 11.245 kilojoules. This is 3 sig figs, 5 sig figs, 4 sig figs. This ended up being 4 sig figs, right? So 3 sig figs. So negative 11.2 kilojoules of energy can be used as work. Any questions about that? So again, anytime you calculate these things, you could always make a balanced thermochemical equation by simply adding it to the end of the reaction that you just calculated. So everybody good? Okay, let's try another. So this is number 40 from chapter 18. It says carbon disulfide reacts with hydrogen to produce methane, and hydrogen sulfide is a byproduct. It says calculate del H, del S, and del G at 25 degrees Celsius for this reaction. And then I'm going to do that because then we'll come back to all of these other things. So how am I going to calculate del H, del S, and del G for all of these? Well, if no other information is given, we're just going to use the summation laws. And since I got to calculate all three, what would be the easiest way to calculate all three? Would I use all three summation laws for del H, del S, and del G? I mean, you could. I would certainly not mark it wrong, but is there an easier way? Because using the summation law takes a while. Why don't I just calculate del H and del S and then use the relationship del G is equal to del H minus T del S? We've seen that we get basically the same answer. So let's do it that way. Again, if you would have calculated it using del G as well, the enthalpies of formation, or the free energies of formation, again, that's perfectly a good way of doing it. It's just you're wasting time, okay? So I'm just going to look up the free energies of formation in kilojoules per mole to calculate del H. I'll look up the absolute entropies in joules per Kelvin per mole, okay? And I'm going to do it for all of them. Again, just to save time. Once I'm in the tables, I'm just going to look up the values. And again, if you were going to use the free energies of formation, I would have looked them up at that as well. Okay. So for the for the carbon disulfide, that is 116.7 kilojoules per mole. I can already see that this is the elemental form of hydrogen, so I know that's 0. For gaseous methane, that is negative 74.6, and for gaseous hydrogen sulfide, negative 20.6. And again, I would have actually gotten, I should have went down. I would have done both of these at the same time. So the absolute entropy was 237.8. Now, for hydrogen, the elemental form, the entropies are not 0. So I actually would have had to look that up anyway, which would have been 130.7, the absolute entropy for gaseous methane, 186.3, and for that of the hydrogen sulfide, 205.8. Now I'm just going to use the summation laws for both of these. I'm not going to rewrite the equation, right? It's just the enthalpies of formation of the products minus the enthalpy of formation of the reactants. So del H then is going to be equal to the 1 mole of methane at negative 74.6 kilojoules per mole, plus the 2 moles of hydrogen sulfide at negative 20.6 kilojoules per mole. And we will subtract from that the 1 mole of carbon disulfide at 116.7 kilojoules per mole, and add to that the 4 moles of hydrogen, but that is at 0 kilojoules per mole. So that just goes away. This is the moles cancel the whole way through. So we're gonna get
Question.
Yep.
How come you looked up the S value for the H2? If it's
because we're going to need it, because we're going to calculate both the change in, see, it's asking for the change in enthalpy, change in entropy, and change in free energy. So when I was in the tables, just to save time, I just looked up the values, all of them.
Okay.
Okay. And again, remember for the elements, the absolute entropies are never zero. They're always going to be some positive number. Okay. And so that's why I looked them both up, because I'm going to do this again, but for the change in entropy. Okay. Okay, so I would plug this all into my calculator then, and I'd get negative 232.5 kilojoules. We have mixed operations. So this here, what? This is going to be 41.2. So that's still 3 sig figs. And the rest of these are the same. So they're all one pass. So your change in enthalpy then would be 232.5 kilojoules. Okay. Now we're going to use the summation law again, but this time for the change in entropy. So again, it would be the 1 mole of methane, right? So the 1 mole of methane at 186.3 joules per Kelvin per mole. Then the 2 moles of the hydrogen sulfide at 205.8 joules per Kelvin per mole. And then we're going to subtract from that the 1 mole of carbon disulfide at 237.8 kilojoules per mole. And we're going to add to that the 4 moles of hydrogen at 130.7 kilojoules per mole. Again, the moles cancel the whole way through the calculation. Okay. Whoops, and these are wrong units. These are joules per Kelvin and joules per Kelvin. Okay. So now you'd plug that into your calculator. Again, we have mixed operations. So this is times 2. So what that's going to be 411.6. Again, joules per Kelvin, and it's 4 sig figs, so 4 sig figs. And then we have 4 times 130, so that's going to be what, 4, 5, 22.8. Let me make sure that's correct. Yep, so 522.8, and that would be joules per Kelvin. And again, to there. So plug all of that into your calculator. That'll be negative 162.7 joules per Kelvin. We have 1 passed, 1 passed, 1 passed, 1 passed, so 1 passed. So negative 162.7 joules per Kelvin would be your answer for del S. Okay. Any questions so far? Now, again, you would have been perfectly okay to use the enthalpies, the free energies of formation and the summation law for the change in free energy. Or I think an easier way at this point is del G is simply equal to del H minus T del S. Since I already got these two values, and doing this is such a pain in the butt, I'm just going to plug these values in. Negative 232.5 kilojoules minus the temperature. Well, it's at 25 degrees Celsius. So add 273.15 to that. That's 298.15. And it's 1 passed. So that's in Kelvin. Now our entropy, right, that needs to be in kilojoules. So I'm going to divide that by 1,000. So this is the same thing as negative 0.6127 kilojoules per Kelvin. So this is negative 0.1627 kilojoules per Kelvin. I can see that my Kelvin and per Kelvin cancel. Now I'm going to have kilojoules minus kilojoules. Well, this number here is going to be negative. So again, we got this mixed operation here. So this is going to be negative 48.509 kilojoules, and that is to 4 sig figs. Okay, and then again, take this number and basically plus, right? Plus that number. And so that's going to give you a value of negative 183.99 kilojoules. And that is going to be 2 passed and 1 passed, so 1 passed. So the free energy change then is negative 184.0 kilojoules. Okay, so negative 184.0 kilojoules at 25 degrees Celsius. Any questions about that? Okay, now the second part of this question says, well, calculate the free energy change then at 1,425 degrees Celsius. How am I going to do that? How am I going to do that?
Well, you still have your del H and your del S. So
Okay.
then you just recalculate your del G, substituting in the new temperature.
Okay, so and it's actually a little bit of a different equation too,
Okay.
because it is del G of T. And this is important because by writing that, you're saying that there's some uncertainty in this number. Okay.
Okay.
And again, that of course is just del H minus T del S, except this time this is a non-standard temperature. We're doing this at, what did it say? 1,425 degrees Celsius. So 1,425 degrees Celsius plus 273.15 will give us the temperature in Kelvin. And that is going to be 1,698 Kelvin. Okay. Okay, so now I can plug this in. So again, we already calculated del H, like you said. It is negative 232.5 kilojoules. We're going to subtract from it. So here's our value of 1,698.15 Kelvin. And then entropy, again, we're going to have to use it in kilojoules per Kelvin. So negative 0.1627 kilojoules per Kelvin. So our Kelvin and per Kelvin cancel. Now we have kilojoules minus kilojoules, but it's negative and negative. So we're actually going to add this number. And this number is going to come out to be negative 276.289 and kilojoules. And it is going to be 4 sig figs. And then plug, this plus this into there. And that's going to give you a value of 43.789 kilojoules. Let's see, this is 1 pass, this is 1 pass, so this will be 1 pass. So your final answer would be 43.8 kilojoules. 43.8 kilojoules. And this was at, what did we say? 1,425 degrees Celsius. Okay, so what can you tell me about this reaction at 25 degrees Celsius? Is it spontaneous or non-spontaneous?
It is spontaneous.
Yeah, right. We have a negative free energy change, so it's spontaneous at this temperature. And what about at 1,425? Is it spontaneous or non-spontaneous?
Non-spontaneous.
Non-spontaneous. Now, this question didn't ask this, but at what temperature does the reaction go from being spontaneous to non-spontaneous or vice versa? How would I calculate that?
Would you... So non-spontaneous, could you just put your del G T at 0.
Yeah, exactly right. So
Yeah.
del GT equals 0 at this temperature. I think
And then
spontaneity is spelled wrong. Oh, it's an EI. Okay.
and then solve for T.
That's right, right? And again, I want to see this on your exam. I want to see that you understand that we're setting that to 0. So now 0 equals del H minus T del S.
Can
So
you bump your paper up a bit?
oh, I'm sorry.
Thank you.
Trying to keep all the numbers there, but I can't. Okay. So now we're just going to rearrange. So I'm going to add this to both sides. And then finally, I'm going to divide both sides by by del S, which of course that cancels. And so T then is equal to del H over del S. And again, we've already calculated the del H and the del S. And again, remember, the unit's got to be consistent. So I'm going to put them both in kilojoules since I already have them in kilojoules. Okay, so now the kilojoules cancel. I have 1 over a Kelvin, so our units are going to be Kelvin. The number should always be positive. Okay. So that's going to give me a value then of 1,429.01 Kelvin. And they're both 4 sig figs, so that'll be there. Now, chances are, when I ask you this question on the exam, I'm going to want it in degrees Celsius. So to go from Kelvin to degrees Celsius, I'm going to subtract 273.15 from that. And that's going to give me then 1,155.86 degrees Celsius. Again, 1 in front. So this would equal 1,156 degrees Celsius. This is what we would call the crossover temperature or the temperature of spontaneity. Is this the maximum or minimum temperature of spontaneity? So this again, think about this. We know that del H is negative, and we know that del S is negative. When is this reaction spontaneous, at high or low temperature?
Spontaneous at low, so
So is this the
that be your
minimum?
max?
That is going to be our maximum temperature of spontaneity. Okay, any questions about that?